welcomed Professor Lubomir Skala, talking about Lie-Admissible algebras and mathematical statistics. Please, Professor Skala.
First, I would like to thank Professor Kuladar, all the organizers, Professor Santiago, for organizing, supporting this nice conference. In my talk, I will discuss relation of quantum mechanics and mathematical statistics and some other things. Why mathematical statistics? Physics is about measurement. It means measure quantities, make averages, calculate mean square displacements, and so on. So it is the reason why I start with mathematical statistics, which has the corresponding apparatus to describe such measurements as we do in physics. Okay, so it is the outline of my talk. First, I will introduce the so-called Fisher information. It is one of the basic quantities in mathematical statistics, and it appears that it is related to many questions in quantum mechanics. I will show then how it is related to the wave function, to the kinetic energy. In fact, it can be shown that a part of the kinetic energy in quantum mechanics is the Fisher information. Then I will talk about uncertainty relations. Again, I will show that uncertainty relations, as we know them in physics, especially Heisenberg uncertainty relations, it is very similar to relations or inequalities which are known in mathematical statistics. These are relations for the Fisher information and the so-called Rao-Kramer inequalities. So that there is close relation in many fields. Then I will talk about Klein-Gordon equation. It appears that Klein-Gordon equation can be obtained from the requirement that the Fisher information is invariant with respect to transition from one inertial state to another, from one inertial system to another. That means if we require that the Fisher information is constant during transition from one coordinate system to another one, you can obtain Klein-Gordon equation. Then I will show that using the ideas from mathematical statistics, it is possible to replace the Heisenberg uncertainty relation by two new uncertainty relations which are stronger than Heisenberg uncertainty relation. So that is, I think, interesting result. I also will give example of these uncertainty relations. I will also discuss equality sign in the uncertainty relations because it is interesting even from some applications. Then I will talk about commutation relations. And I will discuss both standard commutation relations and deformed commutation relations. Okay. It somehow shifted. See, this is here. Is it possible to? Mathematical statistics, it can be arbitrary function, reasonable function. And we assume that it is normalized. And we also assume that it behaves reasonably. Okay, now if we take this normalization condition and perform integration by parts in a simple way. Then, due to this assumption, we can neglect or this term is equal to 0, and we get such simple equation. It is just trivial equation. Now we can use the Schwarz inequality and put u and v like this. It is very easy. And we get from the Schwarz inequality such a relation which reminds Heisenberg uncertainty relation. This is something like mean square displacement of the coordinate. There is some quantity here. And what is important, this quantity is called Fisher information, so that we have such, I would say, uncertainty relation. It is in general form, it is called, it is more complex, and it is possible to derive the so-called Ramra inequalities. And it is appeared that it is somehow related to the Heisenberg uncertainty relations. Okay, so to get to compare the inequality for the Fisher information with the Heisenberg uncertainty relation, we write the wave function in the form where S1 and S2 are real functions. It is always possible. Okay. Then the probability density has such exponential form in terms of this function S2. And then the Fisher information can be rewritten in this form. Okay? So you see we have the probability density here and something like Laplace or second derivative. It is not, we have not a Laplace here, but we have the first derivative, but the square, and it can be transformed into Laplace. Okay. So that we see that this Fisher information is obviously somehow related to the kinetic energy. Okay. So using again this form of the wave function, we can rewrite the usual quantum mechanical kinetic energy into such a form. It looks very similar to the previous formula for the Fisher information. There is only one difference here. It is this term, and there's some constants here. So we see that we can split the kinetic energy in quantum mechanics into two terms. The first term is, I would say, generalization of the classical energy from the Hamilton Jacobi theorem. Yeah. Here, of course, we have some probability distribution, so that we make average over some probability distribution, and Hamilton action is replaced by S1. And the second part, it is proportional to the Fisher information. So that we see that the information is a very important part in quantum mechanical kinetic energy, and we can even say that it is very important because due to this term, the kinetic energy of the bound states cannot equal 0, because they go to 0 at infinity, so that the derivative is different from 0, and it is very important property which we know from quantum mechanics. Now, uncertainty relations. Again, we write the wave function in this form. This is well-known uncertainty relation with well-known quantities in the usual notation. And again, similarly to the kinetic energy, we can split this mean square delta P squared into two parts. This is very similar to the kinetic energy. The first part has this form. Again, we see that this part has something similar with something common with classical mechanics. It can be shown that this function here represents momentum. This is mean momentum, and so that this is mean square displacement of the momentum, and it can be it has a classical sense. This is second part, which is again proportional to the Fisher information. Okay, so the Fisher information appears also here in Heisenberg relations. We come to such equation, and since this variation is arbitrary, we can come to conclusion that this parenthesis must be 0. Okay, so then of course we don't know what is this constant, but if we introduce mass of the particle and put speed of light here and the Planck constant, we get the well-known equation. And such a procedure can be repeated for other equations of motion. For example, for the Dirac equation, and one can derive the Schrödinger equation as a non-relativistic approximation to the Klein-Gordon equation, and so on and so on. And now I will show that the Heisenberg constantity relation can be replaced by two stronger relations. In fact, it is very simple. The idea flows from what I showed before. First, I take U and V in the Schwarz inequality like this, and I get directly from the Schwarz inequality such relation. It is for the first part of the delta P squared, and you can see that this part was somehow related to classical mechanics, yeah? And in agreement with this, the right-hand side, which is in fact covariance between coordinate and momentum. Okay, it can be understood as the standard covariance defined in mathematical statistics between coordinate and momentum. Then we see that this right-hand side can equal 0. Of course, it is non-negative, but it can equal 0. So that it is, so to say, classical part of the Heisenberg uncertainty relation. Yes, for classical momentum, or some generalization of classical momentum, and there is no Planck constant here. Okay, now the second relation can be derived very similarly. We use these quantities in the Schwarz inequality and get such formula. It looks complicated here, but by playing with this integral, it can be shown that it equals the well-known constant h bar squared by 4. Okay, so that we have, instead of the Heisenberg uncertainty relation, we have two separate uncertainty relations. One has its analogy in classical mechanics, and the second one is purely quantum. You see, we have only S2, and S2 gives the envelope of the wave function. So that this uncertainty relation is independent of this quantity S1, which gives momentum. So that this is really quantum quantity because it depends on the envelope of the wave function.
Clear?
Well, there's nobody else. I agree with your beautiful presentation, with one only exception. When you said that you failed, no, you did not fail. Because you have made the deformation on a particular case of hadronic mechanics. So you have made the first that I know, the first lifting of statistical mechanics according to the hadronic mechanics. So it's not a failure. It's the first time.
When I was writing this presentation, I thought I failed, but now I see it was okay. It was okay.
No, but from this stage now, here's the point. When you are at a purely quantum mechanical level, there is no possibility that you can introduce entropy or thermodynamics, because formulation, what quantum and statistics subject, first a single non-unitary transport, and you get the foundation, and then you have a dual non-unitary transport.
I saw that it is possible.
It is, the first will be very interesting. Keep me informed, please.
Okay.
It will be great, great advance. Thank you, Mr. Chairman.
Any other comments? Oh, Professor Johansson.
Well, to me this seems an important lecture and raising very profound questions and probably solutions. Because you depart from Fisher information and pure mathematics, probability mathematics, and from there you deduce, for example, you deduce basics of quantum mechanics, such as the quantum equation and the Dirac equation. And we also say that stronger uncertainty relations, stronger than the Heisenberg uncertainty. They have a nature where which is important for information transfer, and that information is not spread. I think that's very important. And the question is, applications of these stronger uncertainty relations than Heisenberg's. Do you imagine applications beyond quantum mechanics? That's part of my question.
Okay.
And related to this, that it seems perhaps that you look at the wave function as such, as some kind of physical manifestation of a mathematical structure that, well, it has some probability mathematical laws that are realized, manifested by the wave function. So the wave function becomes some kind of carrier for a higher, deeper mathematical structure, and of the other. So if you could explore it.
You could see from this presentation that it is necessary to measure only the envelope of the wave function. And I am not experimentalist, but I think that it should be achievable. So that if instead of standard experiments, we make experiments in which we use only the envelope of the wave function, not the complete wave function, then we could make use of these advantages like the equality in the uncertainty relation. And also, if you will be able to measure only the form of the wave packets in optical fibers, then again it would not spread. So that I think it is important point, and till now these results are not so old. So till now there was no experiment done in this direction. Yeah. And the second question was the wave function. Yes, from our point of view, the wave function is not anything abstract. It is just mathematical representation of quantities which have real physical meaning, probability density and probability density current, so that at least from this. Thank you. Please, I thank you.
That's beautiful.
Okay, we are.